This is Mika Seppälä. Hello everybody. In this video I discuss the comparison test that can be used to show that a certain series converges or that some other series diverges. One part of the comparison test says that if AKs and BKs are positive and AK is always at most BK, and if the series formed by the terms BK converges, then also the series formed by the terms AK converges. This is a useful result that allows us to study the convergence of complicated series. This result has also a counterpart which says that if the series formed by the terms AK diverges, then also the series formed by the terms BK diverges. The comparison test to study the convergence or divergence of series is based on the comparison theorem. This comparison theorem has two parts. The first part, comparison theorem A, states that if AKs and BKs are non-negative, AK at most BK for all k, and if the series formed by the terms BK converges, then also the series formed by the terms AK converges, and that the sum of the series formed by the terms AK is at most the sum of the series formed by the terms BK. This last statement is completely obvious because if each BK is greater than or equal to AK, then also the sum of these terms BK is greater than or equal to the sum of the terms AK. So the real problem here is to show that the series summation k from 1 to the infinity AK converges. In order to show that this series converges, we have to study the partial sums of this series. And we observe that these partial sums, which are of the form a1 plus a2 plus and so forth am, form an increasing sequence, since as m grows, we add non-negative numbers to this partial sum. So because AK is greater than or equal to 0 for all k, the partial sums Sm form an increasing sequence. Next, recall that we assume that each AK is at most BK. This means that the partial sum Sm, which is a summation k from 1 to m AK, is at most summation k from 1 to m BK. Then we assumed that this series summation k from 1 to the infinity BK converges. Therefore, this sum k from 1 to the infinity BK is finite, and this is an upper bound for all these partial sums Sm. So we conclude that each Sm is first of all non-negative and at most summation k from 1 to the infinity BK. And here this last bound is a finite number. So this means that these partial sums, summation k from 1 to m AK, form a bounded increasing sequence. But a bounded increasing sequence has a limit. We conclude that the limit, that is the summation k from 1 to the infinity AK, that is the limit as m goes to the infinity, summation k from 1 to m AK, exists and is finite. And this means that the series summation k from 1 to the infinity AK converges. This concludes the proof of the comparison theorem part A. The comparison test can also be used to show that certain series diverges. This is based on part B of the comparison theorem. Here we assume as before that AKs and BKs are non-negative and that AK is at most BK for all k. The statement of this part B of the comparison theorem for series is that if the series summation k from 1 to the infinity AK diverges, then also the series summation k from 1 to the infinity BK diverges. In order to show that the series summation k from 1 to the infinity bk diverges, we have to study the partial sums of this series formed by the terms bk. Now each bk is greater than or equal to ak. This means that the partial sum, summation k from 1 to m, bk, is greater than or equal to the partial sum k from 1 to m, ak. These partial sums Sm for the series formed by the terms ak form an increasing sequence because each ak is greater than or equal to 0. If this increasing sequence were bounded, then it would have a finite limit. And that would mean that the series summation k from 1 to the infinity ak converges. But we had assumed that that series diverges. Therefore, since that series summation k from 1 to the infinity ak diverges, the partial sums Sm form an unbounded set. And this means that the limit of these partial sums k from 1 to m, ak, as m goes to the infinity, is the infinity. And since each sum k from 1 to m, bk, is greater than or equal to sum k from 1 to m, ak, it also follows that the partial sums for the series bk have the infinity as their limit. Therefore, we conclude that the series summation k from 1 to the infinity bk diverges because its partial sums grow arbitrarily large as m grows. In this example, we have to show that the series summation k from 1 to the infinity, 1 divided by 2 to the power k times 2 plus sine of k converges. We do that by the comparison test. More specifically, we will use part A of the comparison theorem. And in order to be able to do that, we first observe that for all integer values of k, 2 plus sine of k is always between 1 and 3 and never reaches these bounds because for all integer values of k, sine of k is greater than negative 1 and less than 1. This means that the general term 1 divided by 2 to the power k times 2 plus sine of k for this series is at most 1 divided by 2 to the power k. This is so because all these expressions are first of all positive, and then we replace 2 plus sine of k by its lower bound 1. If in a positive expression we make the denominator smaller, then the whole expression becomes larger. Therefore, 1 divided by 2 to the power k times 2 plus sine of k is less than 1 divided by 2 to the power k, and it is of course also positive. So this double inequality holds for all integer values of k. Next we observe that the series summation k from 1 to the infinity 1 divided by 2 to the power k is a geometric series whose first term is 1/2 and whose ratio of terms is also 1/2. This is a convergent geometric series. And since this upper bound for the series summation k from 1 to the infinity 1 divided by 2 to the power k times 2 plus sine of k converges, then we conclude that also this series summation k from 1 to the infinity 1 divided by 2 to the power k 2 plus sine of k converges by the comparison theorem A. Therefore, we have shown that this series in this example converges. In this example, we show that the series summation k from 1 to the infinity of 1 divided by k times 1 minus sine squared of k diverges. We do that using part B of the comparison theorem, and to this end we first observe that for all positive integers k, 1 minus sine squared of k is always between 0 and 1. It does not reach these limits, so 1 minus sine squared of k is always positive and strictly less than 1 for all integer values of k. Therefore, k times 1 minus sine squared of k is always less than k. And this means that 1 over k is less than 1 over k times 1 minus sine squared of k for all positive integer values of k. And now the harmonic series summation k from 1 to the infinity 1 over k diverges. We know that. And therefore, since the terms of this series 1 over k times 1 minus sine squared of k are larger than or equal to the terms of the harmonic series, also this summation k from 1 to the infinity of 1 divided by k times 1 minus sine squared of k diverges by part b of the comparison theorem. This concludes the proof. In this video, we have discussed the comparison theorem to study convergence or divergence of series. The comparison test for series is the following. Assume that AK and BK are non-negative and that the terms AK are at most BK for all k. Then, if the series formed by the terms BK converges, that is, if sum k from 1 to the infinity BK converges, then also the sum k from 1 to the infinity AK converges. And if the series formed by the terms AK diverges, that is, if the sum k from 1 to the infinity AK diverges, then necessarily also the sum k from 1 to the infinity BK diverges. This is the comparison test.